Good morning. This is VR Seshagiri Rao, Associate Professor in the Department of Electronics and Communication Engineering. Today I am going to give a lecture on Introduction to 8051 Microcontroller. So what is a computer? A computer is a multi-purpose device that can read binary instructions from memory and it processes the data as per the instructions and it provides the result. So it is a programmable device consisting of hardware and software. So what are the various components of the computer? A computer has a memory, output device, input device, and also it has a CPU. The CPU contains the control unit, arithmetic and logic unit, and the registers. And the input device is something like the keyboard, and output device is like monitor. And memory, the program is stored in the form of bits 0 and 1 in the memory, and the instructions are fetched from the memory, and the CPU, it processes the result and gives the output. So as the technology moved from large scale integration to very large scale integration, it has become possible to build the microprocessor, memory and IO devices on a single chip, and this is called the microcontroller. See, the difference between microprocessor and the microcontroller is microprocessor has the CPU and general purpose registers and the control unit and the arithmetic and logic unit, and the microprocessor fetches instructions from the external memory, and in the case of microcontroller, the memory and IO devices and all these things are built in the same chip. How this has become possible? This has become possible because of the revolution in the VLSI technology. So as the technology progressed, we are able to accommodate more number of gates, more number of components on the single chip. So we are able to accommodate the memory, A to D converters, DTA converters, and serial and parallel IO interfaces, timers and counters on the same chip. So this is a typical functional block diagram of a microcontroller. So it has the CPU, and of course it has the oscillator which provides the basic clock pulse, and it has the interrupt control block, and RAM, ROM. RAM is used for the data memory, ROM is used for the program memory, and it has the timers and counters, and it has the serial port and ADC and DAC and IO ports. So this is the typical block diagram of a microcontroller. Now let us see the important features of the microcontrollers. Suppose the 8031, 8051, 8052, these are all the microcontrollers which are made by the Intel. So if we take the 8031 microcontroller, it has an on-chip RAM of 128 bytes and program memory. There is no program memory, there is a written ROM-less. The speed is 12 MHz and there are 2 timers and counters in that, and the number of IO lines are 32, and it has UART. UART is Universal Asynchronous Receiver Transmitter. So it has built-in UART. And coming to 8051, it has 128 bytes RAM and 4 kilobytes of ROM, and of course it also works with the 12 MHz clock, and there are 2 timers and counters, and the number of IO lines are 32, and it has UART. And 8052 is similar to 8051, only the difference is it has more ROM, 8 kilobytes of ROM. So it is double the capacity of 8051 microcontroller. And coming to the 8751 microcontroller, it has 256 bytes of internal RAM, and EEPROM, it has 8 kilobytes of EEPROM, and other features are same, 12 megahertz clock and 32 IO lines, and it has IARE. Okay, and of course the number of timers and counters are 3 here in 8751. And 8751, the difference is it has more EEPROM, that is 32 kilobytes of EEPROM, and it works with more clock frequency, 12 to 24 megahertz. So it is more faster. And 89C61 2, it has a 64 kilobytes of flash. It has 64 kilobytes of flash, and it has on-chip RAM of 1K. And it works with more faster clock frequency, that is 22, 33 megahertz. And it has 3 timers or counters, and it has 32 IO lines, and it has IARE. And 89C252, it has 256 bytes of RAM and 8K flash, and it has 2K EEPROM. So the program memory it is of 2 types, flash and EEPROM. And the microchip company also has made the microcontrollers. It is 16C74 and 16F874, and these have 192 bytes of RAM and 4K ROM, and it works with 20 megahertz clock, 3 timers and 32 IO lines, and it has USART. USART is Universal Synchronous Asynchronous Receiver Transmitter, and also it has 8-bit ADC and serial parallel interface. So 16F874, it has 256 bytes of on-chip RAM, 8K ROM, and it also works with 20 MHz clock, 3 timers and counters, and 32 IO lines, and USART it has, and it has a 10-bit ADC. ADC is analog to digital converter. Now these microprocessor or microcontrollers, they are configured into 2 different architectures. The 2 different architectures are von Neumann architecture and Harvard architecture. See, the microprocessor or microcontroller, both of them have the program memory and the data memory. So how they are connected with CPU? So based on that, the configuration is classified into von Neumann architecture and Harvard architecture. So in von Neumann architecture, the data memory and program memory are connected using a single set of address and data lines. Whereas in Harvard architecture, for program memory there is a separate address and data bus, and for data memory there is a separated data bus. So there are more number of routes available between the memory and the CPU in Harvard architecture, which facilitates more faster computations or calculations. So the MIPS is millions of instructions per second. Millions of instructions per second. So the MIPS is more for Harvard architecture. So as it is shown in this block diagram, this is a von Neumann architecture. You can see here, this is a program memory and this is the data memory, and there is separate data and there is a single set of address and data buses connecting it to the CPU. So here you have lesser speed. The program memory and data memory, both of them have to share same address and data buses. That is von Neumann architecture. Now coming to the Harvard architecture, as you see here, the data memory has its own data and address bus, and the program memory has its own data and address buses. So there are 2 sets of address and data buses. So data memory has its own address and data bus, and program memory also has its own address and data bus. So this facilitates more faster calculations. So the MIPS is more in Harvard architecture. And the microprocessors and the microcontrollers, they are also classified in a different fashion. The different method is RISC and CISC architecture. So in RISC architecture, it is called as reduced instruction set computer, and CISC architecture is called as complex instruction set computer. So the microcontrollers with a small instruction set, they are called as reduced instruction set computers, and the microcontrollers which have a large instruction set, they are called as complex instruction set computer. And 8051, it is an example of CISC machine, and microchip PAC 16F87X, it is an example of RISC machine. Now let us see the comparison of RISC and CISC. So in RISC, the instruction takes 1 or 2 cycles, and in CISC, depending upon the instruction, it takes more than 1 or 2 or 3 cycles also. So instruction takes multiple cycles in CISC, whereas in RISC, it takes 1 or 2 cycles maximum. And in RISC, you have only the load or store instructions to access the memory. Whereas in CISC, you have variety of instructions to deal with memory. So in addition to load and store instructions, the memory access is possible with other types of instructions also. And in RISC, the instructions are executed by the hardware. Whereas in CISC, the instructions are executed by the microprogram. And in RISC, the instructions have fixed format, whereas in CISC, the instructions are variable format. And as far as the addressing modes are concerned, in RISC we have only few addressing modes, whereas in CISC you have more addressing modes. And in RISC you have only few instructions, whereas in CISC you have large instruction set. And most of them have multiple register banks in RISC, whereas in CISC there is only a single register bank. So you have more number of registers in RISC machines, whereas in CISC you have less number of registers. So for a given application, you can easily write the program because the instruction set library is less in the case of RISC, and the programmer need not remember the full instruction set, and he can easily write the program, but the length of the program is more in RISC. Whereas in CISC, the instruction set library is very large, and the programmer can write an efficient program by using variety of instructions, and the code length ultimately it comes short in case of CISC. Now coming to the computer software. So what is the language of computer? The language of computer is zeros and ones. So a set of instructions written in a specific sequence for a computer to solve a task is called as a program, and software is a collection of the programs. And how the program is stored in memory? It is stored in the form of zeros and ones, and these are called as the machine instructions. And the machine instruction program is also called as object code. And assembler, what is an assembler? Assembler takes the simple source code and it converts it into zeros and ones, and you get the object code. So here the source code contains one word or two word instructions, and the assembler converts this source code into the object code. Whereas to convert the high level language into the object code, a compiler or interpreter is used. So the compiler or interpreter converts the high-level language to the machine code or machine language. It is also called as the object code. Now, what is an embedded system? See, embedded system is a combination of hardware and software for a specific application. What is the difference between the microcontroller and the embedded system? The microcontroller has the CPU, the memory, and few I/O devices like ADCs, DACs, etc. But the microcontroller, it gets life once the program or the software is loaded into the memory. So once the program is loaded into the memory, it becomes an embedded system. So embedded system, it is defined as the combination of hardware and software for a specific applications. So embedded systems, these are used in consumer electronics, food processing industry, chemical plants, and everywhere. Cement plants, biomedical equipments, telecommunications, security. Now embedded systems are omnipresent. They are used in almost many applications. And the embedded software which is executed is called as the firmware. Now, what are the characteristics of embedded systems? So, based on the processor and the software, there are various types of embedded systems, and reliability, cost effectiveness, low power consumption, fast execution time, and efficient use of memory and processing power. These are all the characteristics of the embedded systems. What is the reliability? Reliability is the probability that the product performs its function for the specified period of time. So reliability of hardware and software is most important in embedded systems. So the embedded system should reboot and rest by itself without human intervention during failure. So the core design of hardware and software is given importance in case of embedded system to meet these requirements. Now, what are the other characteristics of embedded systems are cost effectiveness and low power consumption. So, as the embedded systems are developed to meet the requirement of specific applications in mass markets, so product cost has to be kept at minimum. Okay, and to meet the requirements, the system is developed using first the prototype system is developed using general purpose processor, and then application specific integrated circuit is used to reduce the hardware and cost. Low power consumption, because the embedded systems are backed by battery power, so the power consumption has to be less so that you get maximum life. If the power consumption is more, very frequently you have to charge the battery. So as the most embedded systems are battery operated, so the power consumption has to be kept less to increase the battery life. And so this can be achieved by reducing the number of hardware components and by designing the processor to go to sleep mode when there is no operation. So in sleep mode, the power consumption is less. And the other characteristics of embedded systems are fast execution time, efficient use of memory, and processing power. So fast execution time, in real-time embedded systems, certain tasks must be performed within a specific time. So to meet the performance constraints of real-time systems, special operating systems are used. So to fulfill the performance requirement, the code should not be more, it should be optimal. And the software is generally developed using high-level languages, and some computationally intensive units are developed using assembly language. And the memory also has to be used efficiently, as the embedded systems contain only ROM and RAM without secondary storage. There is no hard disk or anything. So the memory has to be used very efficiently, and the operating system what you are going to use, you should occupy less space so that the memory can be used for application. The remaining part of the memory can be used for application program. So most of the microcontrollers and digital signal processors, they are available with on-chip flash memory so that you can do the modifications. Or if any new updates are there, so new updates can be ported into the embedded system if you are using flash memory. Now, processing power. So the number of instructions which are executed per second, that is called as the processing power of the microcontroller. And most of the processors, they execute one instruction in one clock cycle. So as I mentioned, the processing power is mentioned in terms of MIPS. MIPS is million instructions per second. The more the value of MIPS, the more it is better. Next, coming to the embedded system architecture. So embedded system is a dedicated computer-based system for a specific application, and the software is embedded in the program memory. And the hardware of embedded system, it consists of CPU, memory unit, input unit, output unit, the application specific circuitry, and the communication channels. So this is the block diagram of a typical embedded system. You have the CPU, input devices, output devices, you have RAM, ROM. So in RAM we store the data, in ROM we store the application specific program, and there are of course the communication channels and application specific circuit. So what is application specific circuit? Suppose if you are using a robotic controller, so there you have to specific application circuit like the high voltage drivers, like that hybrid voltage drivers, and all those things are included in the application specific circuit. So the important processors that are used in embedded systems are these are the microprocessors, and these are the microcontrollers, and these are the digital signal processors. So 68HC triplex, that is Motorola, and 8086 is the microprocessor, and these are all the microprocessors that are used in most of the embedded systems. And these are the microcontrollers 8051, 80196, 89661, and microchip are PIC 16F84, PIC 16F874. These are all the from the microchip, and ARM7 and ARM9. So these are all from, these are all the advanced RISC machines, and in some embedded systems the DSPs are also used. For example, the Motorola series 5600XX and Texas digital signal processors and analog devices digital signal processors are also used. So these are all the important processors that are used in embedded systems. So what are the design challenges in embedded system? So the embedded system designers and developers have the design challenges like the co-design, embedding an operating system, and optimizing the code. See, code optimization is very important because it results in efficient processing speed. And co-design. So this in an embedded system design, the task is implemented using the hardware and software. So the design engineer has to decide which module needs to be implemented in hardware and which module needs to be implemented by the software. So the hardware design imposes the constraints of size and cost, whereas the software implementation imposes the constraints of the memory size. So if your code is not optimal, you need a large memory to store the code. But if the code is optimum, you can save on the memory space. So software implementation imposes the constraints of memory size and the performance. And to design an efficient embedded system, code design is definitely a challenge. And choice of an operating system. The operating system should occupy lesser space. So there are special operating systems which are used for the embedded systems, and they are chosen in such a way that they occupy less memory space. And optimization of code. So in the design of embedded system, memory and execution time, these are all the important constraints, and it is a challenge for the designer to optimize the code to meet the constraints. And in the olden days, development of application, it was done using assembly language. So debugging and maintaining the assembly language program were very difficult and time consuming. So now most of the development of embedded software is done using object-oriented languages. And these embedded operating systems are designed to work on semiconductor memory with limited processing power. So as there is no secondary storage device, so we have to depend mainly on the semiconductor memory. So the advantage of using operating systems in embedded systems are the program can be written in high-level language, and object-oriented programming languages, particularly C++ and Java, are extensively used for embedded software development. So the programmer can focus on application program rather than on the memory and I/O management program. Now, non-real-time and real-time operating systems. What is a non-real-time embedded operating system? So these are suitable for soft real-time embedded systems to perform tasks like memory management, I/O management, and etc. And they are not suitable for hard real-time applications. Examples are embedded Windows XP and embedded Linux. Whereas in real-time operating systems, these are suitable for hard real-time operating systems. So these are used to provide the necessary system calls for real-time deadlines. So what are the examples of real-time operating systems? Like RT, Linux, and VxWorks and OS by 9. So these are all the examples of real-time operating systems. In military applications, for airborne and space applications, VxWorks is popularly used. And for mobile and handheld operating systems, embedded Windows NT, Windows CE, Palm OS, and Symfony OS. So these are used. So in embedded systems, the OS and the application software, they are integrated and stored in the memory of the embedded system. And in most of the embedded systems, it is important to perform some computations in a time-bound manner. So such embedded systems where strict deadlines are imposed, they are called as real-time or hard embedded systems. Suppose if you are using an embedded system for a nuclear power generation, suppose a valve has to be closed when the pressure is more than the specified limit. So it has to exactly act when the pressure exceeds the limit. So it has to meet the deadline. The valve has to close at the deadline. Otherwise, catastrophe is going to happen. So these things are called as hard embedded system. So it has to work in time-bound manner in a strict deadline. And what are the different aspects that are to be considered in choosing a microcontroller? So in we have to consider different aspects like speed, the amount of ROM and RAM, the number of I/O ports, the timers, size, packaging, power consumption, and easy to upgrade. So these are all the various things which are considered while choosing a microcontroller. And also we have to consider the cost per unit and the noise of environment and availability of software development tools like assemblers, debuggers, C compilers, emulators, simulators, technical support, and all these things are also are to be considered for while choosing a particular microcontroller. And wide availability and reliability sources of microcontrollers are also there. And ROM type 801, you have to see there are different types of microcontrollers. As far as the ROM characteristics considered, in 8031 there is no ROM, and in some microcontrollers you have EEPROM. In some microcontrollers you have a combination of flash and EEPROM. So depending upon your application, you have to choose the microcontroller. And these are all some of the comparison between the 8051 family members, which we have discussed earlier also. So 8051, it has 4 kilobytes of ROM and 128 bytes of RAM and timers are 2. Whereas in 8751, you have 4K EEPROM and 128 bytes of RAM. And in 8752, you have 8K EEPROM and 256 bytes of RAM and the timers are 3. So this is the basic pin diagram. Or this is how 8051 or 89C52 microcontroller looks like. It's a 40 pin device, and 8051 it has 4 kilobytes of internal RAM as we have discussed, and it has 128 bytes of RAM, and it has 4 8-bit I/O ports. That means there are 32 I/O lines and 2 16-bit timers, and it has one serial interface, and 64K external memory can be added to it in case it is required, and 64K external memory also can be added in case it is required. So the basic 8051, it has an 8-bit CPU and it is optimized for control applications, and it has the capability for single-bit Boolean operations, and it supports 64 kilobytes of program memory and 64 kilobytes of data memory. And it has 4 8-bit I/O ports, and of course it has UART, and it has interrupts, and it has on-chip calculator, on-chip oscillator. And what are the differences between 8086 and 8051? Basic differences. So microprocessor and microcontroller. What is a microprocessor? It is a general purpose device, and that is called as CPU. And microcontroller, it has, in addition, it has memory also. And microprocessors are almost commonly used as a CPU in microcomputer systems, and microcontrollers are used in small minimum component designs performing control-oriented applications. And microprocessor instructions are mainly nibble or byte addressable, whereas microcontroller instructions are both bit addressable and byte addressable. So you have bit addressing capability as well as byte addressing capability in case of microcontroller. And microprocessor instruction sets are mainly intended for catering to large volumes of data, whereas microcontrollers have instruction set catering to the control of inputs and outputs. And microprocessor-based systems are complex and expensive, whereas in microcontroller you have built-in RAM, ROM, and built-in devices, so they are simple and cost-effective. The cost is less in microcontroller-based systems. And the instruction set of microprocessor is complex with a large number of instruction set, whereas in the case of microcontroller, the instruction set is very simple and with less number of instructions. For example, the PIC microcontrollers have only 35 instructions. And the microprocessor has a 0 status flag, and the microcontroller has no 0 flag. So with this, I conclude today's session on Introduction to 8051 Microcontroller. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.